Hello. We are saying we are tackling a question on radioactive decay. This is a second application on first order differential equations to these problems. So we are saying a particular radioactive substance has an half-life of 20 days. After 50 days, only 100 milligrams have remained. Find the amount of the radioactive substance initially. So we should find uh, p of 0. Okay, so we will mention what we have. So we are saying the general knowledge is when the time is 0. Okay, we have this condition where the amount of the radioactive substance equal the initial amount of the radioactive substance. Then we are saying after time has elapsed, we know after 50 days. Okay, we should expect after 50 days we should expect the amount of this radioactive substance equal 100 milligrams. Okay, but we have an additional information with the half-life. We're saying initially we said half-life is the time taken by the undecayed substance, to go to a half. Okay, a half the initial value. So we are saying if we have the half life, so I'll write t a half equal 20 days. Okay, I'm expecting the original amount, okay, to go to a half. So this will be my uh, amount at that time. After certain 20 days, we should have the amount remaining to this radioactive sample as P0 over 2. So maybe just to mention, this will we will take this as our initial condition. Okay, take this our initial condition, which will able it will enable us to calculate the value of C. Okay, so we calculate C from this point, and then from this concept of half-life, we will able to calculate the value of our decaying constant, which is lambda. Okay, so we'll be able to calculate our decaying constant lambda from this expression, from this. So we'll get that. So from there we should first solve this differential equation, because we know from the differential equation, so you're saying from the differential equation that the rate of decay, okay, the rate of decay should equal k lambda, okay, or lambda t, or kt. Okay, so should equal lambda t. So from this point we are saying, okay, from this decaying law, we are saying the rate of which this substance is decaying should equal lambda multiplied by the original, multiplied by the quantity of this radioactive sample at that time. Okay, so should equal lambda p, not lambda t. Sorry for that. So we are saying once we have this, so let's separate our variables and solve for this differential equation. So we're saying separate, so the variables. Okay, so check my video on our second video on how to solve first order differential equations. So from this case, I'll divide by p. I'll get dp upon p should give me lambda delta t. Okay, so if I take the integral of both sides, I should get ln of p should give me lambda t plus a constant. Okay, so continuing that, we are saying for us to solve for p, we should take the exponential of both sides. So p, if I take the exponential to this side and then exponential to this side, I should get e raised to lambda t multiplied by c. Check why I've said so. So here there's a multiplication at this point, so e to c, which gets absorbed, it gets absorbed to c. Okay, that's why I've written this c at this point. I've clearly explained that in my previous video, so I'll be quick to this point. So from this point, we are saying for us to find C, okay, we had our initial condition. Check my video on our initial value problem. So we're saying for us to get our C, sorry, we are saying let's use the initial condition. We were saying time equals 0 when P equals P0. Okay, so substituting these inside this equation, we are saying at P0, okay, when time equals T, we should get P0. So P initial should give us E raised to lambda multiplied by 0. This will go to 0 multiplied by constant. So from these, we're getting that our constant equal the initial value. Okay. So from there, we're saying let's perform, let's get back to the equation. So this is our first equation and substitute our value of C. So we're saying P equal P0 multiplied by E raised to lambda T. Okay. So these are our first equation that should keep in mind. So we are saying first to solve for k, okay, first to solve for k we should include this condition here where we are having the half-life. Okay, so we are saying p equal p0 divided by 2 after a certain period of time, which is 20 days. Okay, so we are saying p should equal p0 divided by 2 should equal p0 multiplied by e raised to lambda multiplied by the half-life. Okay, so we are trying to solve for lambda at this point, so this will cancel this. I will remain with a half should give me e raised to lambda 20 at this point. Okay, should get lambda 20. So from there, how will we perform this? We are saying if I take a half, I should take the ln of this side and the ln of this side. Okay, so let's perform the ln. If I take the ln of this side, I should also take the ln this side. So if I take the ln of 2, I should get ln of a half should give me e ln e. I should remain with 20 lambda. Okay, so if I take that, so from this case we are saying this is ln of 1 minus ln of 2 should give me 20 lambda. Then we are saying this goes to 0, so I'm saying negative ln of 2 should give me 20 lambda. Okay, so from this point, if I take the ln of 2, which is 0.69, okay, but we are solving for lambda, so I'm saying lambda equal negative ln of 2 divided by 20. Okay, so if we solve for this, we are saying k lambda should equal negative 0.03465. Okay, now having this knowledge, so we have our lambda. So let's go back and substitute in our general equation. So this is our general equation. So let's substitute the value of lambda at this point. So we're saying p. So because we were told after a certain period of time, which is 50 days, we should get our remaining radioactive sample as 100 milligrams. Okay, so this is our general solution. So we are saying after a certain period of time, we should remain p equal, let me just write p equal p0 multiplied by e raised to lambda t. So from this one, we're saying P represents the remaining sample of the radioactive material. So which is 100 milligrams that have remained should equal P0, which we are looking for. Then multiply that by exponential to the value of lambda, which is negative 0.03465. Then after a certain period of time, because we're dealing now with 100 milligrams which had remained after 50 days. Okay, so the time there should be 50 days. So for me to get my p0, I should get 100 multiplied by e raised to 0.03465 multiplied by 50. Okay, why have I write positive? Because if I take this to this other side, it's simply division, so I can divide by e raised to negative, which I can take it back and multiply that by the positive side, which is the value. So for me, I'll get my p0 as 565 0.48, because it's in milligrams, should be in milligrams. So our initial amount of this substance before it underwent a radioactive sample equal, so our initial value equal 565.48 milligrams. Okay, so please like, share, and subscribe to my channel. Have a lovely day.